So what we're going to do today initially is start off with something fun, which I just got done the other day, that kind of steps back and looks at some parallel streams issues. And this is going to demonstrate some interesting ways to use collectors for various purposes. We've talked about a variant of this example before, but this is some new stuff, and it really shows off a neat feature. So this particular example we're going to look at is in my EX36 folder in my GitHub repository under Live Lessons Java 8. And it's going to show the difference in overhead between basically combining and collecting results in a parallel stream versus a non-parallel stream, using both concurrent and non-concurrent collectors for various types of Java set implementations, both concurrent and non-concurrent. And so it's going to show off some really, really interesting stuff. The way it's going to work is we're going to have the complete works of William Shakespeare, and we're going to collect them, and we want to put them in a set so that we only have the distinct words of William Shakespeare. And we're going to do it in a couple different ways, using hash sets, which don't order the data, and tree sets, which do order the data. And then we're going to take a look at some different ways of implementing collectors, both concurrent and non-concurrent, to do all that. So we come in here, we warm up the fork join pool just so the test will be, they won't bias for the second one that runs, because the first one will have to pay the cost of creating the threads, because threads are created in the common fork join pool in a lazy fashion. So we're first going to run the collectors tests that are unordered. These are the ones that just use some type of hash set, which is, of course, is unordered. And the way this is going to work, we're going to have 4 different sizes of input data. We're going to have 1,000 words initially, then 10,000 words, then 100,000 words, then finally up to 1 million words. It turns out that Shakespeare doesn't have 1 million words, but those are the ranges we're looking at. And we're going to see which of the different approaches works better or worse. And what we're going to do here is we're going to start out by getting the works of Shakespeare. So we have this file over here, which is complete works of William Shakespeare. Believe it or not, there's actually an MIT project that has all the works of Shakespeare, I think there's something like 37 plays and a bunch of sonnets or something like that. So that's what we get there. And we're going to go ahead and read those things in. And the way we do this is we load the file that contains the works of Shakespeare. We convert the works of Shakespeare into a giant string of Shakespeare. It's a Shakespeare that contains a single string that has all the works of Shakespeare. We then go ahead and use a splitter, and this is defined here. The splitter is going to basically say, split the input or split the contents of this string that has all the works of Shakespeare in it into words, ignoring white space. So if you come back over here, you can see that we're going to use a regular expression to split the input up into essentially a stream of words that are going to be unique. So we get the stream of words. We get rid of any words that are empty. We're only going to have limit of them, so that'll be 1,000, 10,000, 100,000, 1 million, and so on. And then we collect the results into a string. So we end up returning, or actually it's really into a list of char sequence objects. So the results comes back as char sequence. And there's reasons for doing that we don't have to care about right now. All right, so now we've got ourselves a list of all the words of Shakespeare, split up, ignoring white space. Then we're going to go ahead first, and we're going to collect this into a hash set, and we're going to do it sequentially. So to use a sequential stream to collect all the words into a hash set. Of course, a hash set will be unique, so we'll have all the words of Shakespeare uniquely as a hash set using sequential streams. Then we're going to do the same thing, and we'll look at this method in a second. We're going to do the same thing, except this time we're going to collect all the words of Shakespeare using a parallel stream into a hash set. So that's, in this case, the hash set is going to be a non-concurrent collector. But it'll be done in parallel, which is perfectly valid. And then to make it even more interesting, we're going to use a concurrent hash set implementation, which will collect things sequentially, which is kind of a silly thing to do because you would use a concurrent hash set if you're using parallel streams, but we're going to do it just to see what the overhead is. And then the final thing we're going to do here is we're going to use a concurrent hash set for a parallel stream. So that's really the one that we want to focus on because we think that'll be the fastest, because there'll be no need to merge the various hash sets as the collect is working up in the various threads. So let's take a look at the methods that do this. This is time stream collect to hash set. Let's see what it does. We figure out a little diagnostic, whether we're doing this parallel or sequential. And then we're going to go ahead for a certain number of iterations. We take the words that are passed in as a list and we convert them into a stream. We use a dynamic programming trick to turn the stream into a parallel stream if we need to. And then here's where we do the stuff that's interesting. We take the word stream, we lowercase everything just to do something. It's not the most interesting thing to do, but it does something, burns a little CPU time. So it makes Q more than 0 if you look at the NQ formula. And then we collect the results into a hash set. And remember how hash set works, whether it's for, hash set is not a concurrent data structure. It has to be called in a single thread of control. And toCollection returns a non-concurrent collector. So even if we have a parallel stream, this will still be running in one thread at a time. And then the incremental hash sets will be merged together to give you the final hash set. So there'll be a lot of merging going on. That's the key thing to remember about the non-concurrent collectors is there's lots of merging. And if you have data structures like a hash set that are non-trivial to merge, then you'd expect to have a fair amount of overhead doing that, which, as you'll see, we do. Okay, so then let's pop back up here and go look at concurrent hash set. And this is very similar to before. We take the list of words, we turn it into a stream, we turn the stream into a parallel stream, and once again, we take the words in that stream and we lowercase them either sequentially or in parallel. The difference is this time, instead of collecting into a hash set, we're going to collect into a concurrent hash set. So let's go take a look at what a concurrent hash set is. And you can see that there's a factor method called toSet, and toSet returns a new concurrent hash set collector. Well, that just raises the question, what is a concurrent hash set collector? So here's what a concurrent hash set collector is. So a concurrent hash set collector is a collector that takes items of type T, in our case, character sequences or strings, and it stores them in a concurrent hash set as the one and only accumulator, as you'll see. And then we are going to return a concurrent hash set, which will contain the contents of the merging, or not the merging, the accumulating. So here's the way the collector works. We have a supplier that just returns a new concurrent hash set. I'll show you what a concurrent hash set is in a second. Think of it as a concurrent hash map that only has a key, not a key and a value. And it has all the other properties of concurrent hash set, hash map. The accumulator simply adds the next item into the concurrent hash set. We can assume, as we'll show in a second, that adding is an atomic operation, so we don't have to worry about race conditions. We have a combiner, which in this case is a no-op, because of the fact that we're doing this as a concurrent collector. There's no need to combine anything. And then the finisher is also a no-op because we're just giving back the concurrent hash set at the end that's been accumulated into. And then here's the thing that makes this all work properly. We give the characteristics metadata to say this collector is concurrent, which means there's no intermediate merging of results. Everything goes directly into the one and only concurrent hash set. We say we don't care about ordering because after all, this is a hash set, so who cares about ordering? And we say we have identity finish, which says that finisher can be a no-op. Making concurrent set means that combiner can be a no-op. Making identity finish set means that finisher could be a no-op. And then here's the factor method that makes this thing. Okay, so armed with that, we're now ready to pop back over to where we use all this stuff. And I'm just going to go ahead and run this test, and then we'll take a look at the output. And we'll focus initially just on the concurrent hash set stuff and the hash set stuff. Okay, so if we come up here, we can see the results. We warmed up the fork join pool. We've got 16 cores available. And then here's the part that's kind of fun. So notice we first do these tests with 1,000 words, then we do the test with the first 10,000 words of Shakespeare, then the first 100,000 words of Shakespeare, then all the words of Shakespeare. You may never have known this, but there are 883,311 words in Shakespeare. Not necessarily unique words, because we're going to turn them into a set, and then we'll know the number of unique words, but that's the number of words. In case you're ever on a trivia show and they ask you that. So if you take a look at the results, you can see that when n is relatively small, when there's only 1,000 words, all the different approaches work about the same. In fact, you'll also notice that when there's a very small number of words, the sequential stuff actually is a win, which underscores the fact that sequential programming is a win until n gets big. This is the whole n times q thing we've talked about before. All right, that's pretty cool. So now we've got 10,000 words, and you'll notice that once again, sequential is still a win, and the results are still about the same. Now you'll notice when we have 100,000 words, then parallel starts to win. And you'll notice that the parallel version of the non-concurrent collector is the winner now. So that's the winner. But then when we get to all the words of Shakespeare, at this point, n is very large. Q has stayed the same all the time, but n is bigger. And now you'll see really the key point, and this is the key point about scalability. Parallelism is a bigger win when you get larger n, which I think you sort of knew that, but this just makes that point even more explicit. And so you can see here that what we have is the concurrent hash set is now the winner, and a winner by a fair amount, right? You can see that the concurrent hash set approach is actually doing quite well. And you can see that the parallel non-concurrent collector for hash set does well. So now parallel approaches are dominating, and then the sequential ones are doing worse. And you also notice that using a concurrent collector for a sequential stream is not a win, right? It doesn't really give you anything. It just gives you more overhead because now you have to synchronize on all the updates when it's not necessary to do that. Another thing that's kind of weird, and I'm not sure how far I would take this, but notice that the time for all the words of Shakespeare was actually faster for the concurrent hash set than it was for 100,000 words of Shakespeare. I am not entirely sure where that result comes from, so I would be a little careful interpreting that. That's probably just variance in the timing of these tests. But the big point here is that as n gets bigger, the concurrent collector stuff is a bigger win. All right, so that's part number one.